Okay, we're going to talk about vapor pressures of solutions and then boiling point and freezing point elevation. All right, so here we go, solutions, we got to talk about vapor pressure. And we've seen vapor pressure before, but remember, vapor pressure is just the pressure exerted above a solution by the particles of that vapor, so to speak. So if you add a non-volatile solute, it will lower the vapor pressure of the solvent, because the dissolved solute particles will decrease the number of solvent molecules near the surface. So if you add a non-volatile solute, which can actually mix together, it will decrease how many of them are available to float around. So, because less solvent molecules have a chance to escape into the gaseous phase, because more of them are being used to kind of hold the solution together. At least that's the way I think of it. Now you have what's called Raoult's law, where you have the pressure of the solution, you've got the mole fraction, and then the pressure of the solvent under ideal conditions. Remember, that little circle just means ideal conditions, which is usually 25 degrees Celsius and 1 atm. Now the pressure of the solution is the observed vapor pressure, so it's the vapor pressure above the solution. We've talked about mole fraction, vapor pressure of the pure solvent, and it's a linear graph, so that you get a straight line if you have the pressure of the solution, graphed against the mole fraction of the solvent. Okay, so if you look on page 526, you've got some samples. It says find the vapor pressure at 25 degrees Celsius for a solution of 158.0 grams of sucrose, 643.5 milliliters of water. Glad we don't have to measure that one out. Okay, density of water. Now, I know we say most of the time it's 1. Here's one of those more specific versions. At 25 degrees Celsius, it's 0.9971, which most of the time we're going to use as 1. And the partial pressure of water vapor is going to be 23.76 torr. Again, here's my little caveat here. If this looks confusing, the book will show more steps and will kind of get you from point A to point B. So here's our initial stuff. We're looking for the mole fraction. And this is just going from the volume to the grams to the moles, because obviously we've got to have moles on top. And this is just the moles of water. And this is the total moles. So here's that moles of water again, plus the moles of our other contribution. And there's my mole fraction with no unit, which we like. So then we just plug and chug. We've got our mole fraction times the pressure, which we said they gave us, so we get 23.46 torr for that one. Now for an ideal solution, a liquid-liquid solution that actually obeys Raoult's law, nearly ideal occurs when a solute and solvent are very similar, so similar forces. So volatile solutions are when both components are volatile. Here you've got pressure total. Again, this is a reflection of Dalton's law, and then you also can use mole fraction. So this is also showing you some of those relationships. Deviation from Raoult's law, just to show you some of the patterns we see. A negative deviation, example acetone in water, when the solvent has special attraction to the solute. So when there's a little bit more of an attraction there. The observed vapor pressure will actually be lower than predicted, excuse me, because of the interactions. So that's going to be this one right here, where it's actually lower than where you would predict it to be. Positive deviation, for example, ethanol and hexane, the solvent has especially weak interactions, and so it's going to be a little bit higher. So this is when it's higher, this is when it's lower. This is when it's actually what it's supposed to be. So just some graph. Here's some additional information. Again, vapor pressure is one of those things that it either makes total sense or it just takes a little bit of extra practice. You've got some different samples, and then we have a nice summary table on page 530 that kind of just talks about the behavior and puts it all on one page, which I think is easy to understand. Okay, I'm also going to talk about boiling point elevation and freezing point depression. These are part of what are called colligative properties. Now, colligative properties are unique to solutions, and these properties depend only on the number of solute particles in a solution. So, it's going to depend literally on how many atoms and how many particles are dissolved into a larger volume solution. And it's going to have certain patterns we're going to see. Doesn't depend on the identity of the particles, just how many are floating around. And this is going to include freezing point depression and boiling point elevation that we're going to talk about in this video, and osmotic pressure that we're going to talk about in the next one. Now, boiling point elevation, the name is pretty self-evident here in that it elevates the boiling point, but also that a non-volatile solute will lower the vapor pressure. And if you lower the vapor pressure, you're going to raise the boiling point. So a higher temperature is going to be reached in order to reach the 1 atm of pressure, which defines the boiling point. So the volatile would do the opposite. So a non-volatile solute will elevate the boiling point. A volatile solute will do the opposite. It will lower the boiling point and raise the vapor pressure. Amount of elevation depends on the concentration of the solute. Again, how many particles are there? Now, we've got our equation here. Delta T is the change in boiling point. So remember, this when we solve for this, this is a really simple plug and chug equation, but where people get lost is this is going to give you the delta T. So a couple of things, we almost always talk about water on these, and so those are numbers that we should know, that the typical boiling point of water is 100 degrees Celsius. So if you get delta T and it's 3.5, positive 3.5, then your new boiling point is going to be 103.5 because you got to take into account that original 100 degrees Celsius. So just a little thing. Kb is molal boiling point elevation, constant, and this is usually given to you. And then M is the molality. So this is also part of the reason we had to know those molality concentrations. And a lot of this stuff is on the AP Chem sheet. So graphically, this is just showing you, here's your pressure and your temperature. This is a phase change graph that just shows you some of those things on there and those points. Okay, freezing point depression is going to be just the opposite. Shaka Shiri is going to go into a lot of detail on this stuff too, and we'll do a lot of plug and chug and showing you the math problems. But vapor pressure of the solid and liquid are equal at the freezing point. The non-volatile solute will lower the vapor pressure, so a lower temperature is needed to decrease the vapor pressure to that of the solid. It's a really fancy way of saying that it will depress the freezing point. This is the same reason that we put ice on the roads. Salt on the roads to melt ice, because as soon as the salt and the water mix, it actually lowers the freezing point or the melting point, because it's the same temperature, which allows the solution to melt even though it's at freezing point of water. So the amount of depression, again, depends on the concentration of the solute. Excuse me. Here's our freezing point depression equation. This time this is the amount that the freezing point is depressed. So again, it's the delta T. And just as a reminder, our typical freezing point for water is usually 0 degrees Celsius. So you just have to lower it from 0. So it might be negative 3.5. Kf is a constant. M is molality. Rock salt, like we said, makes ice cream, etc., etc. And here's just the Kb and the Kf for several solvents. I'm fairly certain that the Kb and Kf values for water, which you need. So when you go to do a problem and you go, I don't know, how am I supposed to find that? Oh, sorry. You guys would never do that. When I go find Kb and Kf, you can find them here, or you can also find them on the AP Chem sheet. But the Kb for water is 0.51, and the Kf for water is 1.86. B means boiling, F means freezing. Just FYI. Okay, here's a sample 533. On page 533, wants to find the molar mass of glucose. What? How do I do that? And given I've got 18 grams of glucose, add it to 150 grams of water. Boiling point of the solution is 100.34. Boiling point constant is given. Okay? So I got to go into this equation, and I'm going to find my molality. And I'm going to get moles per kilogram, because that's my molality. Which you may go, ooh, okay, maybe. I kind of see that. I take my moles per kilogram, divide it by the 0.15 kilograms of water. I then, excuse me, can use my molar mass. I know is mass per mole. So once I figure out I have the grams, I have the amount of moles, 180 grams per mole. Boom, molar mass. Clear as mud. One more example. You've got ethylene glycol as antifreeze. Okay, here's our molar mass, 62.1. Needs to be added to make 10 liters of water freeze at a solution of negative 23.3. That's low. Obviously, antifreeze is important because it prevents us from our cars freezing up. There's our density of water. Again, there's that boiling point constant of water, 1.86, or the KB. Plug and chug. I get my molality. I've got my liters of water, then I'm going to go from liters to milliliters, milliliters to grams, grams to kilograms. So then I've got my 10 kilograms of water, my moles per kilogram, and I can figure out how many grams that I had. Okay. Again, clear as mud. Alright, I'm going to do osmotic pressure with the next video.